Well, one of the here's one thing that you know. So suppose you have you know it's the homomorphic image of a three group, right? So this is isomorphic to so if you have your abelian group A, good, that put it at sequence. So the first isomorphism theorem A is isomorphic. Now let me take you another class. Forget the K and forget the A. Can you embed that in an divisible abelian group? You embed it to Q until
that one phase.
That's right. And in fact, I think there's another homo problem on there that probably helps you with that. Because I think there's in there one that says the homomorphic image of the divisible group is visible. So that should probably help.
So you just get like projection and
yeah. See if that shakes the tree out. Okay, other questions?
It's not a question, but I heard an easy way to remember projective and injective modules. They say the projective module is a good basketball player, and the injective module is a giant because everyone can. He's so high, everyone can pass him.
Okay, well, if that works for you, sounds good. So, the last theorem we had last time, we went through that, and we had some important adjectives in the theorem: torsion, free, and finite degenerate, both of which were used. Any finitely generated torsion free module over a PID is free. And if we have not already seen, you'll see in the homework some examples that if you remove either one of these adjectives, this may not be true anymore. Let me give you a corollary to this. If A is finitely generated, okay, module R, then A is isomorphic F sum AT. Now let me tell you what these pieces are, where F is free and AT is torsion, and F is isomorphic to A. And given this isomorphic, that last statement probably shouldn't be too surprising. So this is actually, in a certain sense, a huge piece of the puzzle of classifying finitely generated abelian groups and more generally finitely generated modules over PID. So I'm going to give you pieces of the stuff that you've probably seen before, and some of the proofs I'll sketch, and some of them I may not but I'm gonna do some examples here to kind of remind you what's going on. Let's prove this. So basically, the cool thing is if you have a finitely generated module with PID, you can break it up into two puzzle pieces, a free part and the torsion part. And what we're going to do from here, if we want to take the torsion part, we're going to deconstruct that as well. So why is this true? Well, suppose R is a PID and A is finitely generated as a module. Then we have okay. We have that short exact sequence right there, where AT, this is the set of A and A, such that A are 0 for some is torsion submodule. And as we've seen before, AT is a submodule because I don't even need PID here, I just need that R is a domain, which it is. So far, we haven't used PID yet. Let me point out this. On AT is torsion free. Right. We prove that in the homework? Can't remember if we did or not. We didn't. Let's prove this. This is torsion free. Suppose there exists such that so suppose that what we have here is a torsion element, so I can multiply a non-zero R and R such that this is 0, right? This means RA is a torsion element, right? Because the cosine RA plus AT is 0 plus AT, so RA is a torsion element. So there exists a non-zero T in R such that TRA is 0. But if R and T are 0, then RT is not 0, because after all, we're living in an integral domain. Therefore, A is a torsion element. Therefore, A plus AT is 0 plus AT, and so A mod AT is torsion free. Because we've shown the only torsion element is the 0. Okay, so torsion. Okay, and now we throw this at it, right? Because now, notice that A mod AT is finitely generated because A is, and any homomorphic image of a finitely generated module is finitely generated, and torsion free. So A mod AT is free. Right? So to finish this off, we have this is free, so it's projected. Therefore, since that end is projected, the sequence splits. And in particular, A is isomorphic to AT, correct sum, A mod AT. And that takes care of all the statements that I made in that corollary. Okay. Any questions? Okay. This is actually, so now, let me make the following remark. So let's suppose A is finitely generated over R, a PID. Then A is isomorphic to a three-part direct sum torsion part. I only need to know one piece of information to understand this, and that is how big it is, right? So this is and let me also point out that the free part could be zero. That's it also could be zero.
I don't think you define free modules to have non-empty bases.
No, I also said that on the empty basis, you have the zero module. I want zero to be a free module. Right. So, for example, you would want this theorem to incorporate all torsion modules, finitely generated torsion modules, and we have a torsion point. And this one's a little bit more open-ended. This part is either zero or it's some positive finite number of copies of R. This one right here, I'd like to understand a little bit further. And so how do we deconstruct the torsion part? And this will look familiar. I'll prove a couple of things, but I'll mostly kind of wave my hands at some of this theorem. I'll go through a bit of the proof of this because it illustrates the importance of PIDs. Let A be a torsion module. So as you see, I'm concentrating just on torsion. I'm forgetting about the free for now. Module over the PID R. And suppose we have a non-zero prime. So we'll take a non-zero prime P and let AP be so AP I'm going to define to be the submodule A such that E to the KA is zero. Actually, that'll throw the zero in there for me. Then A actually, I think I can do this. A is less than what we can write something AP, and if A finally generated, then an AP is zero on the circuit. That is AP. When I say almost everywhere in this class, it's like not like an analyst, but like a number theorist, all the finite nature. Oops. Okay, so let's see if we can actually prove this. Okay, the first thing I need to do is let's show the sum. That I first showed that this torsion module must be the sum of all these eight things. How would I do that, right? So I'm showing that if you take all these eight P's as such defined and throw them all together, everything in there. Let me start kind of with short lemma, and I think the lemma will take care of it all. So suppose that we have A and A. Suppose that X, Y are in R with okay. Suppose you have A in A. Now A is the torsion module, right? So it means it's killed by something in R. Let's suppose it's killed by XY, and we can factor XY into two relatively prime pieces, right? Right, okay, so far. So A is killed by XY is zero, and X and Y I happen to be relatively prime pieces. I claim that I can decompose A using this here. Well, yeah, it's on high divisions. What's special about in a PID? What's special about X and Y being relatively prime, having a GCD one? Right, the ideals intersect trivially, but that's true for UFD too, right?
You can write one as a linear combination.
Right, that's the important thing. Here it says R1, R2, and R, such that R1X plus R2Y is equal to 1. And that really kind of takes care of this. So this means that R1X times A plus R2Y times A is equal to A. Right. Now notice that this piece is annihilated by Y. Right? And R2 YA is annihilated by X. Because if I multiply this by Y, I've got that XYA, so it's 0. And if I multiply this by X, I've got XYA, which is 0, right? So in other words, A is in, right? If, so that means sort of modifying this notation. Notice I make this notation only for prime powers, but and so that's why the sum works, because the reason that this generalizes, so this is really all you need. If you have two relatively prime pieces, what happens is you can decompose A into a piece that's killed by Y and a piece that's killed by X, right? Now, more generally, if you have A is annihilated by use this observation to A into and so in general, since anything's going to kill you is a product of primes, because you're in a PID, you have to decompose that one. So that's why that piece works. What about the intersection, right? Because I did say the sum is direct. Well, again, I'll just sketch this out, but note if A is annihilated by X, Y, where GCD of XY equal to 1, um, uh, let me get this. Suppose A so this will be a special case. I'll let you generalize this. Suppose A is an AP and it's also an AQ. So and here I should have said PQ distinct primes. Well, notice that, and actually I'm not even using primes in this. Notice that GCD P to the K, Q to the L is equal to 1, right? because prime powers are still have greatest common factor of one. So there exists R1, R2, and R such that R1 P to the K plus R2 Q to the L is equal to 1 and multiply by A. This is 0, and this is 0, so this is. So, in fact, the intersection of any two of these submodules where you're relatively prime like this is a 0. So the sum is, in fact, correct. And with these observations, it actually follows that if A is finitely generated, you can only have finitely many of these being non-zero. Okay. Any questions on that? Yes.
Here, P and Q only need to be co-primes, right?
They only need to be co-prime. That's exactly right. So, I'm gonna go ahead and skip this up. And I'm gonna work some examples here. Let A be there we go. Theorem 719. So let A be a finitely generated module for PID. Over a PID. Number one, A is the direct sum of a free module finite rank. Free module of finite rank. And a finite number of cyclic torsion modules. These cyclic torsion modules, if there are any, there may be none actually, but if there are any, finite cyclic torsion modules then are isomorphic to R mod TR. With PI and R non-zero, non-units, and P1, P2, P4. And these are called the invariant factors. The invariant factors and the rank of the free part uniquely determine AF isomorphism.
This looks much similar to the factorization of Cn.
That's exactly what it is, actually. It's an exact, it's a very sort of mirror generalization. Um, okay, so number two. Alternatively, the torsion part can be expressed as prime powers in the following sense. As a direct sum of cyclic torsion modules, sum of torsion modules of form R mod P I P P I right, with P I and R prime and E I in the natural numbers, not zero, and the list of primes P1, P2, P, and exponents E1, E2, EP, determine A uniquely. And the collection of PI, EI, these are called the elementary divisors. So for example, I'm going to give you, and I'm just going to do finitely generated abelian groups because it's all the same, it's PID, but as a quick kind of reminder, if you look at Z30, this is already an invariant factor decomposition because it's already cyclic, isn't it? If I did it in terms of elementary divisors, notice I've got 3 primes that divide that. Right? Let's do an example with more meat on it, and let's make sure that I make one that I'll regret. I don't know if you've all ever done this kind of computational stuff, so let's we'll forget about the free part. Z20, direct sum, Z30, direct sum, Z420, direct sum, Z12, direct sum, Z500, sum, Z 686, some C90. That's one that I'm sure that I'll regret. Okay, so I want to determine the elementary divisor and invariant factor decompositions for this random abelian that I made up. So the first thing, do y'all know how to do this? Have you ever done this before?
Yeah. Not at this scale.
Well, so the first thing I like to do is break it down into prime power pieces, right? And then I get greedy after that. So this is isomorphic to, let's say, this is Z4 times Z5. This is Z2, Z3, Z5, right? And really, all you really need to do is think about the way these factor and just break them up into prime power pieces. 420, everybody's favorite day. This is Z4, direct sum Z3, direct sum Z5, direct sum Z7. Looks like Z12 is Z4, direct sum Z3, Z500, and what is that? That's like 4 times 125. So this is Z2, direct sum Z125. Z4. Oh, C4, thank you. And this is 2 times 343. 2, direct sum Z343. And 90 is 2 times 45, so that's Z2, direct sum Z9, sum Z5. Everybody agree with me so far?
I think 343 is divisible by 7. Okay, that's
It is, that's 7 cubed.
okay. Oh, okay.
So, well, I'll do this first because it's easier for the way I think about it. Okay, I'm just going to go through and pick off the primes, right? And I'm going to try to go high to low. So let's look first at 2. I've got 2, 2, I've got 4, 4, 4, 2. Okay, I never get above 4, do I? I've got 1, 2, 3, 4 fours. And what do I have? I've got 1, 2, 3 twos. All three very unmatched. Direct sum. Let's look at the threes. How many threes do I pick up? We've got a 9 and a 3 and a 3 and a 3. So it looks like 9's the highest one. We'll have 3 threes after that. There's my 9. 1, 2. Okay. So far, so good. Let's do the C5. What do I got here? I've got a single 5. I've got 5 cubed and 3 more single 5s. So it looks like a 5 cubed and 3 single 5s. 125, and then 1, 2, 3, 4. 4 of them.
I think you missed one.
Did I miss one? I figured it. Good. Right, I get it right. Okay, the last thing I got is, what do I have? Oh, I just got this loan. No, I've got a 7 to get a single one. And that should take care of everything. So for this one, I would say that my elementary divisors are 343, 7, 125, 5, 9, 3, 3, 3, and 4, 4, 4, 4, 2, 2, 2. Right? Let's see. So how do we do the invariant factors then? I'm going to do this kind of an opposite order. This is oftentimes why I like to do the home divisor first. Although you can sort of do the other one first, but you can now be greedy because what you do is just pick them off. Just pick out the largest primes, right? So this one right here, the first one, the largest cyclic factor, 7 cubed times 5 cubed times 9, 3 squared times 2 squared, right? And the next one is 7, 5, 3, so that's 105 times 4. So it drops quite a bit, doesn't it? The next one, okay, so we're out of these, so we're done with the 7s. 5, 15, 60. Um, 5, 15, there's another 60. And now I'm out of 7s and 3s. See 10. The last one I've got are those just trail end last C2s. There you go. So there's the elementary divisor, invariant factor. Correct. Okay, any questions on that? Okay, so basically, modules over PID so far, it's just been a ripoff of what you all already seen in the fundamental theorem of finitely generated Abelian groups. Like somebody said, hey, really, finitely generated Abelian groups, that's just a finitely generated module over the Z. And the only thing I really care about is Z is a PID, and this generalizes nicely, so there we go. We can do this more generally. But here is what I want to sort of underscore as an application. So this is kind of a big application section, if you will. Decomposition of a linear transform. Not so we're going to use what we've done so far and try to develop something, but first I gotta give you a little bit of background. Definition. N by N matrices over a field. Let me say, uh, A is similar. B, if there exists a convertible by the way, this notation, I just mean N by N matrices over field F, such that you know, this actually looks like, you know, if you studied some group theory, which you all have, this looks like the familiar conjugate notation, and it is. So if you restrict this down to invertible matrices, I mean, not just P, but A and B being invertible, then what this is a conjugation action, right? It means that A and B are conjugate. But this is a more general thing. I'm only demanding that P be invertible because look at the formula, I have to, but A might not be invertible, for example. So I think that is a good place to stop for today, but we will continue. Everybody's seen this definition of similarity of matrices, am I correct? So next time I'm going to tie this all together and we'll start talking about what's this got to do with modules of the PID? How do we tie this together, and what's this got to do with matrices? Any questions? All right. Well, I will see you all on Friday.